Hi all, thanks to the organizers for the opportunity to speak to you about TORAX. And well, the TLDR is that TORAX is our new differentiable Tokamak core transport simulator. It's written in Python using JAX, solves for core transport in Tokamak's temperatures, density, and current diffusion. The reason we developed it is related to the need as we leap towards burning plasmas and the leap from present-day experiments to reactors demands a concomitant leap in the simulation capabilities. We really want to go predict first, using simulation to help prepare pulse schedules, to optimize scenarios, to design and to validate controllers. And for all of these many query applications, it's really a prerequisite to have both fast and accurate simulation. So if we look at integrated modeling, in general, we can see we have a modeling hierarchy. So, there's a whole swath of fascinating research on direct numerical simulation and high fidelity, hero simulations, exascale computing, massively parallel and expensive. This is vital for the ultimate ground truth, at least numeric ground truth, if validated against experiment, not pragmatic for most use cases. For such core modeling and integrated modeling, the workhorses of the past couple of decades have been codes like TRANSP or PTRANSP, JETO, Astra, ETS, or so on, which is comprised of reduced models, so taking sort of fluid assumptions for plasma transport PDEs, where in effect the closures is through coupled reduced models, where the timescale separation is done by treating microphysics as kind of function calls, which populate these coefficients in the transport PDEs, and of course the quality of these reduced models tends to be inversely proportional to their compute time. So tractability and accuracy are conflicting constraints. In addition, there's also a legacy burden with many of these older suites. So what we need for this many query applications with fast integrated modeling is much the same, coupled plasma transport PDEs, where I'm going to focus on the discussion in the plasma core, and coupled surrogate models, which I will discuss. So here, the ML surrogates, their compute time is relegated to the population of the training sets, and could even use higher fidelity models than used in standard integrated modeling. So this is the outcome is, of course, fast, hopefully accurate, and also differentiable, since ML surrogates are nested nonlinear functions which are differentiable. So the challenge is then to actually develop this collection of learned surrogates and an appropriate simulation framework, and that's where TORAX comes in. Just a note on learned surrogates. By this, I mean that the spectrum of models that you need in this multi-physics integrated modeling, ranging from equilibrium, heating, current drive, radiation, MHD, turbulence, neoclassical transport. There have been many such surrogate models already developed, and many more beyond these examples shown here. But it's also important that these are consolidated, because these tend to be different projects for different devices and different parameter ranges, with different methodologies. So it's also important to bring these families of appropriate solutions of ML surrogates for overlapping configuration space for a given machine in one framework. And this is also part of the TORAX project and corollaries. Yep. So as I've been saying, we've really been motivated by these requirements for the fast and accurate modeling, ideally differentiable, which enables nonlinear PDE solvers, gradient-driven, and also powerful gradient-driven optimization techniques, and also learning models from data with parameter identification. We'd like to also easily incorporate these physics model ML surrogates. Somebody who's written a Fortran library for neural network inference, including Jacobians for hand-derived Jacobians in Raptor. I never want to do that again. So easy incorporation of these physics model ML surrogates is a priority, and also modularity. So here we have Python as a feature, provides many of these sort of portability, velocity, and convenience. But then very key here is enhanced Python with the JAX library that provides compilation, speed, and differentiability. So TORAX builds on ideas developed over many years in the fusion community. Sort of the fundamental ideas are not new. It's a differentiable simulation like Raptor, integrated modeling like GenTrack, Astra, TRANSP, and so on. but sort of with a new angle for the modern era. So a word on JAX, I think many are aware, but just a quick primer if not. So it's a library for Python originally developed by Google. Sort of tagline is NumPy on CPU, GPU, TPU. It's really nice because the API is really NumPy-like, but it does have a JIT compiler, which uses sort of XLA under the hood, which means you can also compile the same code on different backends like CPUs or various accelerators. And it also uses a sort of autodiff library to automatically transform functions to their analytic derivatives for all the gradient-driven applications, all in one package. So JAX was developed for ML, but also helpfully due to its NumPy-like API, it's really powerful for scientific computing as well. So here's just a quick example. So this is a classic function used in ML, summing the logistic function. So you get a scalar output, and to transform this logistic function to its derivative. So it's just a function call which transforms it, and then you can call this new function and you get the derivative. And similar transformations transforms functions into their just-in-time compiled versions as well. So one kind of small caveat is that the fact that it's just-in-time compilation means that when you run the code for the first time, there is a compile time overhead, which is for TORAX at least an order of the compile time. This is mitigated though by both sort of on-disk compilation caching, and if you're running many simulations in parallel, you only get this hit only for the first run. So in practice, it's not a big issue, but it's something to be aware of. One other sort of slight caveat on JAX is that ML doesn't have a lot of sort of iterative control flow, whereas PDE solvers do. And it also depends somewhat on the backend that you use. XLA CPU and GPU have different optimizations and performance, but we actually found it's much more performant to sort of reserve the JAX compilation for the bottleneck functions like PD residuals and its Jacobian, and then we keep all the control flow, pre and post processing, and so on is mostly in standard, NumPy, SciPy, and so on. So this actually also eases some development and coupling to wider frameworks. It's not like a JAX black box. You can kind of play with your granularity of what is JAX and what is standard Python, depending on your need. So there's a bit overview of the code. So heat particle current diffusion. We don't have a self-consistent equilibrium solver. We kind of depend on the fact that there is a prescribed time-dependent equilibrium where we have couplings to various backends like Equidisk, now IMAS in development, MEQ, Cheese. There's a growing range of analytical and ML surrogate models, and we aim to make this very modular so that users and developers can sort of plug in their own. We developed our own sort of 1D finite volume method in JAX as part of TORAX, since actually there was nothing really off the shelf that was appropriate and gives a lot of control. We have a couple of different time solving methods. So the most powerful one is using the JAX autodiff, a nonlinear Newton-Raphson solver with adaptive time steps for stability. Or you can also, similar to codes like Jetto and Astra, use a sort of Picard iteration or fixed point iteration predictor corrector solver, which if you use enough steps actually tends to, at least in our experience so far, converge quite well to nonlinear. And modularity is also sort of a goal. So to be able to add new physics modules that sort of other people can run their own time step, put TORAX as a time step function in their own sort of wider workflows, maybe with different source codes or maybe with edge codes and so on. And there's a lot of work recently, especially on making a nice hierarchical and sort of streamlined config with pedantic, with polymorphic data input, a lot of validation and a lot of pedantic tricks to also help ease some of the patterns inside the code. Just one quick word on the governing equations. I'm not going to go through everything, but just to show this is what I mean by these coupled 1D PDEs, the ion and electron heat equations, electron density equation, current diffusion equation. These are flux surface averaged equations, so you get all these geometric coefficients from the from the plasma equilibrium, which comes from outside. and various terms for sources and turbulence and so on, which are calculated by functions in the code when sort of collecting all the terms for the PDE residual. And there's a lot of flexibility in what you can turn on here and turn off, and to prescribe data from outside with kind of polymorphic data options, different boundary conditions, both fixed current and V-loop, all available. And yeah, just a shout out here to like early adopters like Theo Brown from UKAA, who have been starting to use this for step modeling, for example, putting in an edge voltage boundary condition. So this is a non-exhaustive list of the physics model couplings. Most of this is quite standard for integrated modeling. The idea is to use ML surrogates where available. So we have a couple for turbulence now. Qualiqui's neural network from a few years ago, Carol van der Plas's work, and we've actually recently fitted our own. Some words on this later, like a higher dimension Qualiqui's neural network with a more updated version by Philippe Hamel, who's a Google DeepMind, and there's work in progress by UKAA for TGLF neural network. We've recently coupled the MIT's TORAX neural network for ICRH heating. And yeah, these are all kind of plug and play more or less, so more can be added in the future. Where appropriate, of course, we can use fast analytical models like Sauté or Redl bootstrap current models. You can imagine in the near future putting in Facet for heavy impurity neoclassical transport, or Chang-Hinton, or the Liu or the Liu ECCD, current drive model, and so on. For radiation, we have some polynomial fits from Mavren, which is sort of fits to ADAS for line radiation and Bremsstrahlung, and the standard terms for Bosch-Hale fusion power, equipartition, ohmic, and so on. I already mentioned the various options for equilibrium, and really emphasize here the collaborations are key. We're making what we like to think is a natural target platform for the ML surrogates developed for integrated modeling community-wide. We're also thinking a bit about portability for ML surrogates, like with Onyx data storage, and yeah, to sort of ease how this coupling can be done in general. So a bit of a comparison to other integrated modeling codes, so like what I call standard integrated modeling, Jetto, Astro, Transp, and also Raptor is sort of also a differentiable but not auto-differentiable control-oriented code in MATLAB. So we kind of have the best of both worlds in a sense, that we can use different solver methods like lint predictor corrector or Newton-Raphson, and we have the differentiable, auto-differentiable, the power of Python. And one thing I want to actually emphasize a bit, the fact that we can we have these overlapping greens compared to the previous codes, is that in the same framework we can actually have JAX, ML surrogates, nonlinear solver, all the bells and whistles, but at the same time, we can actually turn off these features, go back to standard predictor corrector solvers, couple kind of legacy or higher fidelity, but Fortran or C, even with on-disk data exchange, like there's different ways to do it. But the fact that you can still do standard integrated modeling with TORAX, its main feature is that you can evaluate ML surrogates against their ground truth within the same framework, and avoid all the issues that arise from wondering what's different, the model or the framework that you're using to compare. And this is actually a big advantage. You can also use it to generate the training sets of these ground truth models. So a little bit about verification. So our main point for comparison is Raptor, which is Federico Felici's code from 2011 and onwards, which has really been the inspiration for differentiable simulation in Tokamaks, and sharing similar use cases. So we've been comparing to Raptor. This is for ether-inspired parameters with the same nonlinear Newton-Raphson solver. You can see here a little bit of a current ramp, bit of power ramp with some modulation. The modulation is just to showcase the different timescales of, the confinement timescales or the short ones, with the current diffusion timescale is a longer one. And we generally get, around at worst 4% disagreement. Yeah, that we do not expect perfect agreement due to the fundamental different numerical schemes used by TORAX and Raptor, and we haven't really dug into closing out every last percentage, but we're satisfied with this at the moment. Here's for a bit of a more interesting case. This is for the Spark H mode scenario, the primary reference discharge. So this is using a very nonlinear ML surrogate turbulent transport model. So this it's more challenging for the solvers. And again, we get around 4% agreement. These differences here in the alpha power are just due to the different physics models of ion and electron fractional heating. One important point is the fact that, Raptor is fast, but because TORAX was compiled JAX, we get a bit of an acceleration. So this is nearing real time for this Spark case. This is 11 seconds of Spark with 14 seconds of hold time. Yeah, so no surprise in an open source conference that TORAX is open source, so it has Apache 2.0, which is quite permissive. Yeah, launched almost a year ago now, and please see the online documentation and archive paper that we released, and poke around the repository. So we have a related release. This is actually quite new from about 10 days ago. So this is the QualiKeys, next version of the QualiKeys neural network. So QualiKeys is a reduced turbulent transport model, quasi-linear gyrokinetic transport code by Clarice Bourdelle. And many people in the community have used Carol von der Plassa's QualiKeys neural network 10D. Carol actually released a data set of about 1 billion QualiKeys input-output pairs on Zenodo, but the fit was never done. So we did the fit and released the model in this new Fusion surrogates repository. So QualiKeys 711, it's a combination of a 7D and 11D dataset. The 7D dataset includes the L-mode edge space. The 11th dimension compared to the legacy QualiKeys 10D is in purity density gradients, so it has a bit more predictive power, covers a wide parameter space. It's a very big hyperrectangle, so valid for multiple machines, and also uses better collision operators compared to the legacy neural networks. You can see here that the new one, which is green, compared better to ground truth QualiKeys for these cases. I'm not going to go into QualiKeys validation against experiments. There's a lot of literature on this. With the improved agreement with the ground truth, and the Fusion surrogates repository is it's not a very large library at the moment, but it aims to facilitate kind of how to share these ML surrogates. It's like an inference library. QualiKeys lives there. We already have some contributions from UKAA, TGLF neural network inference code. So it's hopefully a. Oh, no problem. Got 2 more slides. Yeah. So roadmap. Yep. So we'd like to get some more feature parity with standard modeling when new releases coming up, with some more tutorials and so on. And we're looking already applications. We'd like to improve a lot of the physics, go towards multi-ion, purity transport, get a lot more surrogates, demonstrate gradient-driven optimization applications and large-scale batch runs on GPU. And very important to collaborate with the community on getting open source data sets. I was very happy to see the talks about that today for validation and calibration of the model. Yeah, so some initial applications and collaborations are underway. So it's in the CFS Mosaic pulse planning workflow for Spark, and together with GS Pulse. ITER has begun to use it for their pulse design simulator, and they've been coupling IMAS to it. We have some early work by UKAA on using TORAX per step, and a recent project at CEA for West trajectory optimization. Yeah, so very happy to support the uptake in the community. And with this, I'd like to thank you all very much.
Thank you, Jonathan. Great talk. Yeah, just like fascinating work going on there. Really appreciate it. We do have one quick question, then we all better get off to the closing ceremony and remarks. But from Jonathan Broderick, are there any examples on how to expose the autodiff functionality in TORAX?
So what do you mean by expose? You mean to actually look at the to look at the internal representation of the.
It looks like the goal is to compute the gradient of a scalar loss function. But I might let you guys take that offline if that's okay.
Yeah, please write me, and I'll we'll discuss your question and can provide an answer.
All right.